Hello, dear viewers, and welcome to today's session. As artificial intelligence accelerates, its applications are becoming more and more widespread. Among these applications, electronic components and products are the most commonly used carriers, and the reliability requirements for hardware carriers are increasingly high. This is our seventh interview session. Today, we are excited to have invited Engineer Joe, an expert in climate environmental testing and research, to discuss the application scenarios of heat and humidity testing in detail. Hello, Engineer Joe.
Hello, host, and hello, everyone. I'm very glad to be here today to discuss and share with you.
First of all, could you please introduce heat and humidity testing as one of the most important tests in climate environmental testing, and why is it so crucial for electronic components and products?
Sure. Many of our industry colleagues and clients must be familiar with the practical experience of testing. In climate environmental testing, heat and humidity conditions are mainly simulated by controlling temperature and humidity to represent long-term exposure of products in specific environmental conditions, evaluating their resistance to condensation or accelerating aging. The main purpose of this testing is to assess the moisture absorption, electrochemical corrosion, interface stability, and mechanical thermal stress reliability of products or components. There are generally two types of heat and humidity tests. Constant heat and humidity testing. This test simulates long-term exposure of products to stable high-temperature, high-humidity environments. It accelerates material moisture absorption, electrochemical reactions, and more. The failure modes typically include swelling of surface materials due to moisture absorption, or some degradation of insulation performance, corrosion of metals, and the growth of mold. The purpose is to verify the reliability of products or components under high temperature, high humidity environments, particularly in transportation, storage, and usage conditions. Cyclic heat and humidity testing. This test involves cyclic changes in temperature and humidity, which can cause materials to expand and contract, generating stress. The humidity changes can lead to condensation, which can accelerate electrochemical migration. Failure modes may include interface delamination, solder fatigue, coating peeling, or short circuits due to condensation. This test is essential for verifying the long-term reliability of electronic components or products in real-world conditions.
That sounds very professional. Are there any international or national standards for these two types of heat and humidity tests?
Yes, both international and national standards are available. Many of you may already be familiar with them, and most of them correspond to each other. For instance, the MIL STD 2423 standard in the US is similar to the IEC 6068 international standard. There are also specific industry standards, such as ISO 16750 for the automotive industry, National Military Standard 150 for the aerospace industry, and others for the maritime sector. Some leading industry clients have also developed their own standards, which have been adopted or referenced by many others in the field. The standards for constant heat and humidity conditions and cyclic heat and humidity conditions are quite similar in most of the related testing standards. You can refer to the specific documents of the standards for more detailed information.
Since both of these tests have many supporting standards, can you explain the test mechanisms and application scenarios in more detail?
Sure. Let me explain in more detail. I'll break it down into categories. Let's start with constant heat and humidity testing. The failure types typically include 5 areas. The first aspect mainly involves the expansion due to moisture absorption of materials. Material moisture absorption and swelling. This occurs in hydrophilic materials such as epoxy resin and polyurethane, where moisture absorption causes the material to swell, generating stress on the surface. This can lead to issues like PCB delamination with copper foil. Common application scenarios include PCB encapsulation, plastic shell deformation, and optical lens testing. Decline in insulation performance. Moisture infiltration in insulation gaps, such as between coil windings or capacitive dielectrics, can lower surface or volume resistance and increase leakage current, potentially leading to short circuits or local discharges. For application scenarios, such as the insulation of motor windings, the degradation in resistance can lead to issues such as the drift of capacitance in electrical components, the reduction of creepage distance in high-voltage cables, and even the potential for short circuits. Metal corrosion, airborne moisture, along with pollutants like carbon dioxide and sulfur dioxide, can form acidic electrolytes, which interact with metals like copper and iron, causing corrosion. The main application scenarios include issues like oxidation of the pins of electronic components, such as copper corrosion verdigris, rusting of solder joints on PCB boards, and an increase in contact resistance in connectors, among other problems. Electrochemical migration. Under an electric field, ions from materials like tin lead can migrate on the surface of the insulation layer, forming dendrites or causing short circuits. This is common in chip packaging, solder ball shorts, and PCB leakage. Microbial erosion. Microorganisms in materials or the air can decompose organic substances like plasticizers in rubber or resins in coatings, leading to material embrittlement or discoloration. The scenarios mainly include issues such as aging and cracking of rubber seals, chalking of coatings, and fading or blurring of text on labels, among other conditions.
Thanks for the detailed explanation. How do we select the corresponding test type based on these failure mechanisms in practice?
In practice, the choice of testing is based on theoretical models. For constant heat and humidity tests, there are two main models, the Lawson model and the Peck model. The Lawson model is a classic tool for moisture reliability evaluation. It quantifies the influence of temperature and humidity, providing a core theoretical basis for accelerated test design and life prediction. Its core value lies in shortening the overall testing cycle, such as reducing a 10-year test to just a few months and lowering the overall development or validation costs during this period. It's particularly useful for industries like automotive, electronics, semiconductors, and data centers that have high reliability demands. The Peck model combines Arrhenius temperature acceleration and humidity exponent models to quantify the influence of temperature and humidity on device lifespan in semiconductor and reliability testing. This model is particularly useful for IC, LED, and photonic devices. By integrating temperature and humidity stress, it significantly shortens test periods. As for cyclic heat and humidity testing, it applies the Hallberg-Peck model, an extension of the Peck model. It is especially effective for environments with high humidity and condensation, such as tropical rainforests and coastal areas. It primarily introduces an exponential humidity enhancement factor to quantify the onset of condensation effects. The core improvement is upgrading the humidity impact from the original power-law relationship to an exponential relationship, making it more rigorous and capable of more accurately reflecting the localized high temperature, high humidity environment caused by condensation. Of course, the three models mentioned above actually have differences in practical use as well. For example, the Lawson model is more suitable for steady-state hot and humid environments. Its humidity term follows a power-law relationship, so the overall conditions are not particularly harsh. As a result, its application range is somewhat narrower. The second model, the Peck model, also considers the independent effects of temperature and humidity. It is more widely used in steady-state or cyclic hot and humid environments, balancing testing complexity and accuracy. However, its application is limited as it does not account for condensation or the synergistic effects of multiple stresses. The Hallberg-Peck model enhances the impact of humidity, making it more suitable for high temperature, high humidity, and condensation environments. It also considers the synergistic effects of condensation. However, its testing application is more complex and requires validation with multiple data points.
Thank you for the in-depth explanation. How do we apply these models to determine the actual test conditions in practice?
In practical testing, we calculate specific conditions and parameters based on the design of the product and the actual environmental conditions. To make it more concrete, here are a few examples of calculations under constant hot humid conditions. For semiconductor devices like IC chips, we use this model to evaluate metal migration and degradation of packaging insulation in high temperature and humidity environments. For example, for automotive LEDs, using the H3Turb test double 85 conditions with a reverse bias, we assume 500 hours of testing. The Peck model gives an acceleration factor, allowing us to estimate a 15-year lifespan. For IC packaging, if the actual conditions are 25 degrees Celsius and 60% humidity, and the accelerated conditions are double 85, the acceleration factor is calculated to be 150. This means that 1 hour of accelerated testing equals 150 hours of real-world usage, significantly shortening the testing cycle. Here's another specific example. When evaluating the corrosion and failure of mobile phone motherboards or laptop batteries in humid environments, for example, southern or tropical regions, we assume the following conditions: activation factor 0.5, humidity impact 2.2, actual usage 25 degrees Celsius, 70% humidity, accelerated testing conditions 60 degrees Celsius, 90% humidity. With these values, the acceleration factor is calculated to be 80. This means that 1 hour of testing equals 80 hours of real-world usage, effectively assessing the product's reliability in hot humid conditions. Here's a specific example for alternating or combined hot-humid testing conditions. During the cooling phase of an alternating test, for example, cooling from 55 degrees Celsius to 25 degrees Celsius, some products may have surface temperatures below the dew point, leading to condensation, such as on phone screens or automotive sensors. Using the Hallberg-Peck model, we quantify the accelerated failure effects of moisture during condensation. Assuming the following conditions: activation factor 0.6, humidity index 2.5, accelerated testing conditions 105 degrees Celsius, 85% humidity, actual usage conditions -40 degrees Celsius to 85 degrees Celsius, 50% humidity. The calculated acceleration factor is 175. This means that 100 hours of accelerated testing equals 17,500 hours, about 2 years of real-world usage. This approach is effective for assessing the reliability of components, like sensors, in hot, humid cycling conditions. For specific condensation effects, such as testing condensation in automotive electronics, there are industry standards like ECQ 102, which recommend using specialized condensation testing methods, such as cyclic condensation tests, rather than the Peck model. These tests control temperature and humidity cycles. For example, temperature drops from 50 degrees Celsius to 10 degrees Celsius, and humidity rises from 50% to 100% to simulate real-world condensation scenarios. This provides a more accurate assessment of a component's resistance to condensation.
Thank you, Engineer Joe, for sharing your expertise with us today. If viewers have any questions about today's session, feel free to leave a comment below, and we will have our team respond promptly. That's all for today's show. See you next time.
Goodbye.